is Calvin Anderson. I interned at the Suzuki Group today. I'll be transferring to UCSD in the fall, and I'm going to present manufacturing dissipation devices. And we can move on to the next slide. So I first want to introduce the concept of what resistance is. So I'm sure we've all driven a car before, and when we press the car pedal, the car begins to speed up. And when we let it go, our car begins to slow down, whether that by air or the ground. Our car will just slow down by the general concept of friction, right? And so the equivalent of momentum in electricity for an electron is current. And if that is the equivalence for current, then the equivalence for friction in electricity is resistance. And so what we say when we're manufacturing dissipation devices is saying we're trying to manufacture zero resistance devices. And so the implication of this could mean that you drive your car and it'll never slow down. And in electricity, the implication would be that huge problems with energy crisis could be solved, and huge problems with something as small as your phone will never ever heat up again. So we can move on to the next slide. And so this might be a really intimidating slide, and so you can ask me some questions at the end. But in very, very special materials called topological insulators, when we apply a magnetic field and electric current to it, some strange behavior begins to occur. So you can see on the surface, the depiction on the right, that these electrons have a circle in these circles. They try to draw circles, and we call these orbits cyclotronic orbits. And what we want to pay attention to is on the very edge of it, where these orbits they can't really finish their orbit, and so they start to skip along the edges, and we call that conducting edge state. And those edge states are dissipationless, they're zero resistance. And this general phenomenon is known as a quantum anomalous Hall effect. And it has been observed at very, very low temperatures when these topological insulators are made magnetic. And so our twist is to apply a magnetic field, a magnet right next to it, to try to realize it at a higher temperature. And we can move on to the next slide. And so we have our topological insulator here, and then we can click the next button. And when we apply our magnet, we can click the next button. The topological insulator becomes magnetic itself. But unfortunately, this is going to be nanometers thick. It's going to be very, very hard to manipulate. And so we can click the next button. And so we're going to need a substrate, which is millimeters thick, to easily manipulate it. But unfortunately, we can't quite grow directly on top of this. And so we're going to need you can click the next button. We're going to need a buffer layer to grow. And so this is going to be my project. It's going to create this buffer layer to grow this magnet and topological insulator on top of it. And so we can click the next button. And so for this project, we're optimizing this buffer layer. And this buffer layer is going to be made out of a material called cobalt chromate. And this substrate is going to be made out of something called strontium titanate. And we're going to make that STO and CCO correspondingly. And so what do we want for this buffer layer? We want two things. We're going to look for two things: good crystallinity and good surface roughness. And the reasons are going to be in the next slide. So we can click the next slide. And so when we think of atoms like ping pong balls, when these ping pong balls are organized very, very well, you can see on the depiction that it actually stacks very, very well correspondingly. But when these are not organized very, very well in a very bad crystalline state, it stacks very, very poorly. And that's why we want really good crystalline materials, because we're stacking a lot of things on top of one another. And so we want this buffer layer at the very beginning to be very crystalline. And then can we go back? And then on the right, we also want really good smooth surface, because if we have a really rough really rough buffer layer, it's going to imply a really rough magnetic layer. And when we stack a topological insulator on top of it, it's going to be really, really, it's going to have unfortunate consequences because of non-contact points and contact points. And then we can move on to the next one. And so some results. So we're going to manufacture these with something called pulse laser deposition. And so on the bottom depiction, we can see that the laser is going to come in, a very, very powerful laser is going to come in and hit our target, which is going to be made up of a material known as, which is the cobalt chromate, and it's going to create this plasma plume, and it's going to deposit our cobalt chromate on top of the substrate, the strontium titanate. And this substrate is going to be further heated by a heater all the way on the right, and that's what we're going to control, the heater, the temperature that we're going to optimize crystallinity and roughness at. So we can move on. And so in order to characterize our crystallinity, once we have our samples, we're going to need something called X-ray diffraction, XRD. And you can see on the depictions that the X-rays and the atoms are around the same size. And so when they can interact very, very well. And so when we hit these X-rays at the right angle, you can see on the bottom that they actually produce really, really high intensities or very, very low intensities if it's at the wrong angle. And by using X-rays, and by using this process of high intensity, low intensity, we can very, very well characterize crystallinity. And on the next slide. So these are our results for X-ray diffraction. You can see that the X-ray diffraction results, when there's a presence of a peak, it tells us that there's good crystallinity. And all the way on the right, STO, standing for strontium titanate, we see a really, really huge peak, orders of magnitude higher than the other peak. And this is because, as said before, the strontium titanate is millimeters thick, orders of magnitude larger than our nanometer thick sample. And so it's going to produce a much, much higher signal. And on the left, we can see our sample peak, cobalt chromate, and you can see that at 300 degrees, there's no peak. And as we go up to 700 degrees, there's a more presence of a peak, telling us that there's a positive correlation between temperature and crystallinity. And then we can move on.
Calvin, you have about a minute left, so you want to speed through the rest of your slides.
Of course, sorry about that. And so in order to characterize roughness, we use something called AFM. You can imagine this like using your finger to feel things. And we can move on to the next slide. And so this is our strontium titanate, our substrate, and ideally our cobalt chromate will look exactly like this, with the same roughness characterization and the same steps. We can move on to the next one. And so this is our AFM data. You can see that at 300 degrees, it's great. You have the terraces, low roughness, and higher temperatures. It's really, really rough with high peaks. And so our final optimization, we saw a great peak, great crystallinity at 500 degrees, and great surface roughness at 500 degrees. And we can move on. And our future work will be to stack our topological insulator on top of it, test our resistance and magnetization. And we can move on. And I just want to thank my mentor, Delio Mahoney, and the SLI team, Marissa and Sophia, the Suzuki group, and the PI in charge, Yu Suzuki. Thank you. And next slide, just some pictures. Yeah, thank you.